Infinite geometric series. So the question that we are going to ponder today, and it is a bit of a mind-bending question. What is the sum, so adding them up, of an infinite number of positive numbers? What is the sum of an infinite number of positive numbers? So it's not tricky like, oh, we add an infinite number of zeros up, we get 0. That's not what we're talking about. And we're not adding up 1 and -1 an infinite number of times. That's not what we're talking about. So all the numbers in my sequence are positive, and there's an infinite number of them. What is that sum going to be, do you think? Infinity is a really good guess. And I guess I'd say usually it's infinity. But it's not always infinity. And this is the mind-bending part. Like, wait a minute. How can I add an infinite number of positive numbers? Like, we're not tricking you with negatives or zeros. They're all positive numbers. And you not get infinity.
Wait, does it look like that exclamation point?
So that's adding up all the factors.
That's multiplying all the factors. Yeah, the factorial. Let's paint a wall. Like, what? Why are we painting a wall? So maybe in your bedroom you decide you want to paint one wall. And here's what we're going to do. Each day we'll paint half of what's unpainted. All right, we'll draw a picture to make sense of this. So we decide to paint a wall. Day 1, we're going to paint half of it. Let's draw some pictures here. Here's our square wall, just to make life a little easier. So day 1, why knock it out in one day? Let's get tired. Let's stop after one day. Yes. Well, will you? So let's see if we'll get there or not. So there's at the end of day 1. Here's how much. So we painted a half. And that means the total wall, we've painted half the wall. Oops, put that where you can see it. So we're kind of set up a table here. Day 1, day 2, and so on. All right, on day 2, we wake up and half the wall is already painted. That's good news. Now, normal folks would just paint the other half of the wall and be done, but that's not us. We don't want to do that. We want to take it easy today. We only want to paint half of what's left. So here's half of what's left. So there's what we painted today. So on day 2, how much of the total wall did we paint? We painted a fourth, and now how much of the total wall is painted? 3/4. Okay, we're getting close. Like we made progress that day, so we're okay. Day 3, we wake up and we see that 3/4 of the wall is painted. That's nice. And I don't know, this painting thing is getting old, so let's only paint half of the wall today, half of what's left, because I'm getting tired of this. I don't want to finish the job today. Let's paint half of what's left. So day 3, we painted half of what's left. So how much of the total wall did we paint that day? 1/8, yeah. Painted 1/8 of the wall. Now we start to get a little tricky here. How much of the total wall is painted at the end of the 3rd day? 7/8. Let's draw one more picture because this is fun. So day 4, we wake up and we find, of course, that 7/8 of the wall is already painted. Day 1 painting, day 2 painting, day 3 painting. And man, I'm getting really tired of painting this wall, so I only want to do half of what's left. No, I don't want to finish it. I only want to paint half of what's left. This is a terrible way to paint a wall. But on day 4, how much of the total wall did we paint? A 16th. Okay? Good. How much of the total wall is now painted? A good chunk. Well, we painted 1/16 and 1/16 is left. So 15/16 is one way to look at that. Well, I'm tired of drawing, but let's say if we, on the nth day, you know how much of the wall you would paint on the nth day? Look at the pattern. 1 over, not 1 over n, because not 1 over 1, 1 over 2, 1 over 3. 1 over 2 to the n. And if we kind of follow the pattern, that means our total would be 1 minus whatever we painted that day. Now here's where things get a little bit weird. At the infinite day, which you would never get there, right? At the infinite day, how much of the wall would you paint? 1 over 2 to the infinite. What's 2 to the infinite? Really big. What's 1 divided by really, really, really big? A teeny, 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 tiny bit. Like you're at the infinite day, like it's almost all painted, and all you're going to do is like get your toothpick and put a dot right there, and then the next day you'd have to do half of a dot. And then a fourth of a dot. Yeah, I don't know why you just didn't paint this thing the whole time, but so you're headed towards 0. You don't ever get to 0, so it's just like you're headed to 0. And then this is the weird part here. If you could paint for an infinite number of days, how much of the wall would be painted? Yeah, but if you could paint forever.
Just a teeny tiny bit.
But if you could keep painting.
It would never finish. You can only see half.
So the tricky part is, yes, you would never finish because we don't have a real good understanding of infinite, right? Because we think, yes, if you ever stopped, you wouldn't be done. That's true. But if you could go forever, you still wouldn't be done because you would have to stop somewhere. But if you never stopped, this is a calculus idea, eventually, well, not eventually, you would never finish. So would you ever finish? No. You're right. So you would never finish. That's true. But if you had infinite days, which again doesn't really make sense because no one has infinite days. With infinite days, you'd have one complete wall. But if you had infinite days, you would.
If you had infinite days to paint it, it'd never finish.
If you had infinite days, you would have one complete wall.
Are you losing the paint out, or are you just gonna have a wall?
It looked like it's not.
You'd have to start painting the molecules.
You would have to start painting molecules. That's true. That is true. A same type of examples. If I ask you to walk halfway to the door, you want to get up and walk halfway to the door?
Yeah.
If it'll help everyone hear.
Then stand up and walk halfway to the door. So if you walk halfway to the door, will you get there? No, but if you had infinite time, yes. But that's impossible. That's the confusion, is we don't have a real good understanding of infinity because no one has experienced infinity. It's hard to do. But the bottom line is you can take the sum of an infinite geometric series if r, the absolute value of r, is less than 1. So if you're multiplying by a smaller number, right? If you're multiplying by a bigger number, obviously that's not going to work. If you paint one wall today and 2 walls tomorrow and 4 walls the next day and 8 walls the next day, there's no way to add that up. You're just headed toward infinity. But if you're adding smaller and smaller and smaller numbers, then you can get a sum, and it turns out the sum is really an easy equation. The sum is the first term divided by 1 minus r. And this is extra weird because there's no way to check that. Right? Yesterday, if you wanted to check your formula, you just typed it in the calculator, even if it was 10 or 12 or 100 terms, just type them all in and see if you get the same thing. You can't check these because you can't stop. You have to go to infinity. Well, you don't have enough time, right? You run out of time, you run out of space. You can't check the problems. You have to trust the formula. Let's do an example. 40 plus 20 plus 10 plus 5 ... forever. We're always adding a positive number. We're going to add them all up. It's hard to say all because they don't end. All isn't like a closed set. All keeps going forever. So all I need is A1. That's easy. And R, what's R for this one? 1/2. And 1/2 is less than 1, so we are eligible to use the equation. So A1 over 1 minus 1/2. I don't even need a calculator for that one. 40 divided by 1/2 is 80. Which is weird. You're going to add an infinite number of positive numbers and get something that's not infinity. And again,
It'll be a whole number.
well, this one turned out to be a whole number, but it doesn't always. It could.
It's like all, these are all the fractions, like dividing them in half, added up to a whole one, right?
And again, it's really hard to check these because you get down to 1.25 divided by 2, 1.25 divided by 4, 1.25 divided by 8. And that's still not all of them, but I'm getting close to 80. So you can kind of check them, but there's no way to get to 80 because you have to stop somewhere and press enter on the calculator. So checking them is tricky, but not impossible. You get at least an idea that I'm headed toward 80. And if I could go forever in my calculator, which doesn't make sense, but if I could, I would land at 80 if I could add them all up. Let's try another example. The sum from n equals 1 to infinity. So this one's written a little bit differently, but it's an infinite sum. Infinite sum of 5 times negative 2/5 to the n minus 1. Well, again, if I want to use the formula, I need the first term and I need r. So maybe we should just write out a few terms to figure out what's going on here. So for n equals 1, 5 times negative 2/5 to the 0. I like that. I can handle that. That would just be 5. The second term would be 5 times negative 2/5 to the first. Well, that's not too bad because the 5's cancel and we got left with negative 2. So I've got A1. Now I need to find R. But I know that 5 times R would get me A2, right? To get from the first term to the second term, I multiply by R. So 5 times R would land me at -2. So R equals -2/5. Now, if you've done a bunch of these, maybe not even a bunch, but if you've done some of these, you might recognize this equation and say, well, wait a minute, that's A1 and that's R, and not have to do this. But that takes a little bit of work and a little bit of practice and a little bit of experience to do that. So if you're not sure, write out the first several terms, figure out what A1 is, figure out what R is, and then we'll use the formula. So the sum of all those terms would be 5 divided by 1 minus -2/5. I'm not going to do that one in my head. 5 divided by 1 minus -2/5. I bet that's a fraction of some sort. 25/7. So again, a sum of an infinite number of numbers can be a regular number. It doesn't necessarily go to infinity. Let's do one more. 9 plus 12 plus 16 plus, and on and on and on forever. So it's a forever. So I need A1 and I need R. A1's easy because they gave it to me. R, well, let's see. 9 times R is 12. Or 12 times R is 16, but usually you go with the smaller numbers just to make life a little easier. So R is 12/9, which is 4/3. I'd love for somebody to stop me at some point. But if not, we'll keep going. So the formula is A1 over 1 minus R. A1 is 9. R is 4/3. 9 divided by 1 minus 4/3 is -27. Does that make sense for this problem? 9 plus 12 plus 16. So our numbers are getting bigger, and somehow they're all going to add to -27. What went wrong with this?
Oh, it's higher than 1.
Yeah, R is bigger than 1. So right here we should have said, wait a minute, this doesn't work. This has no sum because R is bigger than 1. And the trick is, if you don't recognize that, you can still get an answer. It's the wrong answer, doesn't make sense, but this is what happens to people on the test. They don't pay attention, they just plug in the formula without thinking, and they'll tell me that it's -27. And if their brain had been turned on from the get-go, they would have said, wait a minute, we're adding bigger and bigger numbers, this doesn't work. Maybe they get to here and see that R is bigger than 1. Well, that doesn't work. Or maybe they get all the way to the end and say, wait a minute, I can't add a bunch of positive numbers and land at -27. That's not right. But the reason is, the formula is great, but it only works if R is less than 1.
Doesn't it apply when the R is bigger than -1?
It would also not work if R is bigger than -1.
So that has to be less.
Correct. R, the absolute value has to be less than 1.
Okay.
Another way to say that is that R has to be between -1 and 1. Another way to think about it is that the magnitude of the numbers has to be getting smaller. Right? If you're getting bigger and bigger numbers, it makes sense that you can't add all those up and get a regular number. So your numbers have to be getting smaller. Or their magnitude has to be getting smaller, decreasing towards 0. All right, you have the worksheet packet. It's just the next one. But be careful because they don't all work. So Unit 7 Worksheet 4. This is actually an easier, shorter worksheet. There's only 10 problems. They all use the same formula, but I would add this to the top of this. I give you the formula, but the formula is not really complete unless you include the idea that r has to be less than 1. So I'd put that at the top. Otherwise, you're just going to use the formula and you're going to mess something up because they don't all work. In fact, I would say that 2 of them do not work. So there's a hint. 2 have no sum. So again, be careful. Don't just blindly plug into the formula and trust your answer. Make sure you're paying attention and see that it makes sense.